Welcome to the video. This video will talk about how to solve the popular coin change problem using dynamic programming. So the question we will be answering states, get to that slide. Your quirky boss collects rare old coins. They found out you're a programmer and asked you to solve something they've been wondering for a long time. So we're going to write a function that, given one, an amount of money, and two, an array of coin denominations, computes the number of ways to make the amount of money with coins of the available denominations. So let's look at an example here. We are given an amount of 4, and the denominations of coins are 1, 2, and 3. Essentially, we want to figure out how many combinations will make up 4 cents. So taking these 3 coins, how many combinations of those 3 coins will make up, let's say, 4 cents. We'll call them cents. So let's write this one out and find some patterns here. So the first way we can make up 4 cents here is by using all 1. So all of the 1 cents. All right, they're all going to add up to the 4 cents here. The next combinations that we can use, let's go with 3 ones. Let's go with 2 ones here. 1, 2, and to make up our 4 cents, we're going to need a 2-cent piece. All right, next one we'll do, let's go ahead and use a 1-cent coin, and we'll use a 3-cent coin. And then on this last one here, we can use a 2-cent coin and another 2-cent coin. So all of the combinations of the coins, we have 4 combinations that we can get from these coins. So the solution to this problem is 4. There are 4 ways to make the change of 4 cents when you're given coin denominations of 1, 2, and 3. So before we start finding patterns, let's first review dynamic programming and see what it's all about. When we think about optimization, we should also think about dynamic programming. Dynamic programming is a technique of solving easier to solve subproblems that will lead to a global solution. Now, this technique utilizes guessing, tabulation, and memoization in the design of our algorithms, with optimizing the amount of time used for calculating our solution. I know that's a mouthful, but just think optimization. How do we solve the problem in the shortest amount of time? Now, there are 2 instances in which dynamic programming can be used. The first one is overlapping subproblems. The second one is optimal solution. Now, there's a certain criteria needed to be met. If you're familiar with graph theory, recursion trees and DAGs and all that good stuff there, remember you must have a topological order, and it must be acyclical. So in other words, the question must have 2 things. Let's talk about overlapping subproblems. So this is where the same algorithm recursively solves the same problem. And then we have an optimal solution. Now, this means that the overall solution to the question can be found by using a combination of the solutions to its subproblems. So the optimal or the best solution of the subproblems are all combined to find the optimal or best solution of the original question. So you might ask yourself, how is this any different from divide and conquer? Divide and conquer works by dividing a question or a problem into subproblems and conquering or solving each subproblem. The subproblem solutions will later be combined to reach the solution to the original problem. And that sounds exactly the same, but dynamic programming is really just an extension of divide and conquer. What makes it different is that it uses memoization and tabulation to store results, decreasing the time complexity. That's the optimization that we were talking about. Let's take a look at 2 approaches to dynamic programming. So we have tabulation, which is the bottom-up sort of approach. And then we have the memoization, which is the top-down sort of approach. So with tabulation, the meaning of the word would be to put the info into a table. It could be a table, an array, something along those lines. Memoization just means remember, so we take it from memory. Tabulation has to look through the entire search space And memoization doesn't really have to. Tabulation requires careful ordering of subproblems, and memoization doesn't really care about the ordering. Ultimately, if all subproblems need to be solved at least once, tabulation, or the bottom-up approach, outperforms memoization. All right, now back to the patterns within the problem. So we saw that we took this first coin and we used that coin because it was less than the amount. We used that coin as many times as we could to develop our first array here. In the next array, we used that coin as many times as we could in consideration of that second coin, that 2. So we added up the 1 cent coin 2 times, and we used that second coin to make up the difference. In the third array, we only used that 1 cent coin once, and we used that third denomination that we had, the 3 cent coin, to sum to our amount. Now in the fourth array, we didn't have the ability to use that 1 cent coin anymore. So we moved on to our second coin, our 2 cent coin. The only combination that we had for that was using the 2 cent coin 2 times. Now you can start to see this iterative process of using a subproblem and then combining the subproblems to end up with our ultimate solution. Let's think about this in terms of coding. We iterated through our coin denominator array for each coin given as a parameter. So logically, we stated that if the amount was greater than or equal to our coin, then we took our amount and we subtracted that coin from it. And we just followed this iterative process of taking the amount and subtracting whatever coin we used here to make these 4 arrays. So in order to store these values, let's come up with a list of combinations. Now in this array or this list of combinations, instead of calling these positions here index, let's call them amount. Now the 0th index will be an amount of 0. First index 1 will be an amount of 1. Index 2, amount of 2. And index 3, an amount of 3. And index 4, an amount of 4. I forgot it on that last one. But our amount here is 4. So we're going to need to go up to an index of 4. Now that we're using a combinations array to store these values, let's go ahead and say that the position of the combinations array, so combinations, and remember the index is our amount here. So let's just say amount instead of saying index. So amount. So this position will equal whatever is in that combinations position, that index or the amount. We're going to add that to whatever value is in this position by subtracting the coin. So this may sound a little funny right now, but let's break it down and visualize this. I'm a visual sort of guy. So given this example, we have 4 as our amount. We have the denominations or the coins of 1, 2, and 3. Now, what we have to do is fill in this combinations array. We're going to start with an amount of 0. This is like our base case. So we will input a 1. Oh, that's a crooked 1. We're going to input a 1 here to signify if our amount is 0, there's only one way to make change. And this will never change. The only way to make change for 0, well, you can't make change. None of our coins can be put into 0. So there's only one way to make change for 0, and that is not to provide any change. So this is our base case. It will never change. Let's move to amount of 1. And let's go through our statement now. So if the amount is greater than or equal to the coin. So this is our first iteration. So we're on the first coin, so a 1 cent coin. And the amount that we're going to deal with here is 1. So let's see, is 1 greater than or equal to 1? So it is equal, it satisfies the condition. Let's fill in this second line then. So let's just say C for combinations. I can't really write with this little funky pad that I'm on. So the combinations amount. So we're dealing with 1 as the amount. Now in this position, the combinations amount will be added. Now within these brackets, we're going to say the amount minus the coin. So the amount minus the coin. When we simplify this, we're going to get 0. And we're going to add this to whatever is in this position, index 1. And that is what will exist in index 1. So when we turn these into numbers, there's nothing here there's no value here for 1. So 1 will just be 0. In the 0th index, we have a 1. So let's go ahead and put a 1. When we add those up, 1 plus 0, it's going to be 1. So that's what's going to exist here in our combinations array at index 1. Moving on to amount of 2. So the amount of 2, is it greater than or equal to our coin? And our coin here is 1. And we can say that's true. So let's move on to our statement here. So the combinations, we're dealing with the amount of 2. We're going to set that equal. Combinations at amount of 2, plus combinations with the amount of 2 minus our coin. And we're dealing with our first iteration, so this will be 1. This simplifies to the combination index of 1. We're going to add that in whatever is in index 2. Now again, there's no value here, so we're going to say 0. And in the position or index of 1, we have a 1. Add them up. 0 and 1 will give us 1. So throughout this whole iteration, we're just going to end up with 1. So now let's move on to our second coin. So I'll make a crooked arrow here to show that we are on coin 2, coin of 2 cents. So remember, this amount of 0 here is never going to change. So we're going to leave that 1 as is. So let's move to an amount of 1. So we say, is the amount greater than or equal to coin? No, we're dealing with a 2 cent coin, and the amount we're dealing with here is 1. So that does not satisfy our conditional statement. Therefore, we'll just move on. So let's move on to the amount of 2. So the amount of 2, is it greater than or equal to our 2 cent coin? And it is. So let's fill out our statement. So our combinations amount 2 will equal combinations amount of 2 plus combinations array where coin subtracts from the amount. So we're dealing with an amount of 2, and we're subtracting, the coin is 2, subtracting 2. So let's turn these into numbers here. So when we simplify 2 minus 2, we end up with 0. So whatever is in this 0th position, we have a 1. We're going to add that to whatever is in the second position. We're going to have a 1. Add it up, and this will equal 2. So that means that at index 2, we will have a value of 2. So let's fill that value inside of our combinations array. Next, we move to amount 3. So now we're dealing with this position, amount 3. So 3 is greater than 2. So let's fill out our combinations statement. So the combinations amount or index amount of 3. We'll say we'll add whatever is in combinations array when we subtract the amount. The amount here is 3. And we're going to subtract the coin. The coin here is 2. All right, and if you see what I did here, I just did a plus equal sign. It's a sort of common syntax in Python, just so you don't get confused. So we're going to say whatever is in position 3 here, we're going to add whatever is in position 1. And in position 1, we have a 1. So this statement is just saying 1 plus 1 gives us 2. And that's what is going to rest in position 3 here in our array. So let's fill that in here. put a 2, and move on to amount 4. Now, is the amount 4 greater than 2? Yes, of course. So let's fill in our statement. So the combination with the amount of 4 will add the amount of 4 minus the coin, and the coin here is 2. So this simplifies into the index of 2. Now, whatever lies at the index of 4 will be added with whatever lies at the index of 2. So let's go ahead and put some numbers on these. So what's in index 2 here? We have a 2, and we're going to add a 1. So at our amount of 4, we will input a 3. All right, hang with me, we're almost there. So now we're on our third coin, which is a 3-cent piece. And remember, the amount of 0 is always going to remain at 1. So let's move on to an amount of 1. So is the amount greater than or equal to the coin? No. And therefore, we're going to just move on to that next position. So our new amount here is 2. Is 2 greater than or equal to 3? No. So let's move on to the next position. Is 3 greater than or equal to 3? Yes, we satisfy that condition. So let's go ahead and fill in our statement. So combinations array, and we are at amount 3. We're going to add to this an amount of 3 subtracted by the coin of 3. So we're going to simplify this. We're going to say whatever is at the 0th index, we're going to add to whatever is in that index number 3. When we put some numbers to it, we have index 3, we have a 2 here, and we have a 1 here. So when we add them up, 2 plus 1, that will give us 3. All right, last one. So we have an amount of 4. So is 4 greater than or equal to our coin, which is 3? Of course, so let's fill in our statement. The amount we're dealing with here is 4. We're going to add that to whatever is at the amount 4 minus the coin 3. So this is a C, that is a C. And let's put some numbers to this. So what is in position 4 here? We have a 3. And in position 1, we have a 1. We add those two up, and we end up with a 4. So what we want from this array is this last value here. So we can call a pop. We can call a pop on our combinations array, and that will pop that last element off of that array for us. Now this is the bottom-up approach, a use of tabulation. I chose this because it takes into account that all of the subproblems must be solved, and if we took a memoization approach, we would be using recursion, and this is just faster. You got to think optimization, and it's less complex. So going bottom up on dynamic programming problems is generally cleaner and usually more efficient. Something good to keep in mind. In a way, you might get confused by whether this is a memoization approach or a tabulation approach. I initially thought, isn't this using the memory of a prior subproblem to find the solution rather than building a table from scratch or having a multi-dimensional array? The key difference is the idea of bottom up and keeping track of all the solutions of the subproblems. With memoization, we don't always have to solve all of the subproblems or pay attention to the order of the array. But here we had to keep track of all of the subproblems. I like it like this, but maybe as an extra challenge, you can think of a way to use memoization to solve this problem. Let's get ready to throw down some code to work from the bottom up and track all of our solutions from these subproblems. We're going to combine them all at the end and get our global solution. Let's create steps for what we have done to solve this problem. So looking back, I would say step 1. So for step 1, the first thing that we can do when we're writing our code is let's just create an empty array. All right, and then step 2. Remember this 0th index here. this first element in the array always has to be 1. So let's go ahead and just define that in our array. We're going to input 1 for our amount equal to 0. Step 3, I would say let's go ahead and choose a coin as our parameter. Step 4, what we're going to do is we're going to iterate through our array using that conditional statement. And then in step 5, let's add the number of combinations based on the amount minus the coin. I like creating steps and or pseudocode, if you call it that, to help me solve a problem. It helps me break it down to each line of code is like a different step. Doing this helps me. Maybe it'll help you out in the future. So I'm going to take these steps here and we're going to move over to Python Tutor. Here we will use Python Tutor so we can see what is happening at each step in our array. It provides good visualization of what's going on. So we're going to be given 2 parameters. The first parameter will be amount, and we'll say that's equal to 8. And then the second parameter will be denominations. And let's call this equal to 1, 3, 5, and 7. So what they want is their function that will return the amount of combination used with those coins to make an amount of 8. So let's define this function as change problem. And within this function, we have the amount and we have denomination. All right, so looking at my steps, the first thing I can do is create an array. Let's call this array combinations, like in our example. In this case, I want to build an array with a certain length. Now this length will be the amount that we are given. So to do this, I will fill in 0 8 times within our array. And this will create an array with 8 elements all equal to 0. Looking at step 2, now we need to input 1 for an amount or an index of 0. So to do this, I'm going to say combinations insert. Now within insert, we're going to have index and value. So the index here that we're going to insert into is 0, and the value is 1, because that 0 index is always going to be 1. I should probably mention, don't forget your docstring. Good practice, it's a good habit. Sometimes I forget, I probably should use it a lot more. Also, I think one of my biggest pet peeves is when people just define their variables with a letter. So instead of saying amount, they would say M, or instead of saying denomination, they would say J equals 1, 3, 5, and 7. And to me, this just makes things more complicated. There's no reason to try to figure out what J is going to equal or what M is going to equal. I like this idea of being explicit, and that's why I don't mind writing my variables out. So don't get lazy and define your variables as letters. And just for you guys to follow along, what I'll do is I'll comment every line of this code just so you can see exactly what's going on if you have to refer back to it. So we can say here, we're creating our array of combinations, keeping in mind that each element in the combinations is the number of ways to make an amount. All right, using this insert statement, we're inserting 1 as a base case. There's only one way to make an amount of 0, right? Don't forget. You'll see why in shortly. Now, step 3 is choose a coin as a parameter. Well, let's move to step 4 and see if that helps us out. In step 4, we have to iterate through the array using that conditional statement. So what we're going to have to do is set up a for statement. So let's call it for coin in denominations. All right, and to note, denomination has each coin to be used, and we're going to iterate through this, just like we did in our example. Now, the next thing we're going to have to iterate over is the combinations array. So we're going to use another for statement. So we'll say for the amount, because we're not going to call it index, we're going to call it amount. So for the amount, we know how many times we're going to have to do this, but I'm going to write in the range, and we're going to start at 1, and we will stop at amount plus 1. This for statement is the amount That is the index for each element in our combinations array. Now, this part was probably the trickiest part for me. This is probably the part of the problem that took me the longest to figure out. I was trying to figure out how I could not allow that 0th index to contribute to the rest of the positions in the array. And this was definitely the hardest part of the problem. It's often the little things, right? Okay, now that we've completed step 4, we iterated through the, let's say, arrays. We have to use that conditional statement. Now we have to use that conditional statement. So in that, or under that second array, we're going to say if the amount is greater than or equal to the coin, just like we did in our example problem, then what we're going to do is say that in our array combinations at the amount, we're going to add to it the amount minus coin, right? And this is our step 5. We're going to add the number of combinations based on the amount minus the coin. So after we fill in our combinations array, let's go ahead and print out combinations to see what it looks like. And don't forget, we will have to pop that last element out of that combinations array. So let's go ahead and write the return as combinations dot pop, and that will pop out the last element within that combinations array. So let's make a call to this function, change problem. We're going to input our amount, and we will input our denominations. Let's visualize this execution. So if you pay attention to the arrows here on the left, the red arrow is the next line to be executed, and the green arrow is the line that was just executed. So if we hit next in this next step, we see that it defines the amount. Here's our global frame, defines the variable amount as 8, defines our array, defines our function. Now let's run through our function and see what it does. So here we are creating our array of combinations. Now we have a list of 8 zeros. We're going to insert 1 in the 0th position. Now we are going to iterate on the coins. So we're going to say 4 coin in denominations. We're on coin number 1 here. Let's see what happens in our combinations array. We go down to our conditional statement. If the amount is greater than or equal to coin, we'll check out our combinations array as we go. All right, nothing too excited there, just filled it in with all ones. Let's see how it works on the next iteration, where the coin will be 3. All right, so what it's doing, it's iterating through this array here, and it's checking to see if the amount is greater than or equal to the coin. If it is, then it will execute this line of code, and it's just going to continue to fill in our array. All right, we're on coin number 5. We're dealing with an amount of 1. Notice how this 0th index never changes. This 1's never going to change. And that was with the help of calling start and stop within the range function. All right, now we are on an amount of 1. Our coin is 7. This is our last iteration. Let's see what we get. So here it prints out our array, and our return value is 6. So the solution to our problem is there are 6 different combinations that will reach an amount of 8 using these coins, the 1, 3, 5, and 7 cent coins. All right, let's just take a look at that one problem that we manually completed. So we have an amount of 4. Our denominations are 1, 2, and 3. So when we run this, we are left with this output. We're going to pop that last value, and that would be our return value. So here we're left with a return value of 4. All right, so that's it for this video. I hope you got a little refresher of what dynamic programming was, when it's used, and how it's used to solve the change problem using a tabulation or a bottom-up approach.